The nuclear atom. J. Thomson suggested that the atom was rather like a plum pudding, with a sphere of zero mass and therefore zero density, positive charge, through which moved the negatively charged electrons that he had discovered. In 1909, Ernest Rutherford was responsible for this experiment, which was to mark the end of the plum pudding model of the atom. He took a thin piece of gold foil, a polonium source, which is an alpha emitter. It was encased in a lead block with a hole in the front. The alpha particles would travel out along this axis here towards the gold foil. A thin sheet of lead with a small hole in the centre ensured a very accurate narrow beam of alpha particles. The whole experiment had to be done in a vacuum, as alpha particles are stopped by a few centimetres of air. There was a microscope which was able to travel all the way round the outside of the experiment, and on the front of this was a zinc sulfide screen that would glow when hit by an alpha particle. This was the alpha detector. The expectation, based on the plum pudding model, was that the alpha particles should easily smash their way through the small number of atoms in the gold foil. It was, however, found that a small number of the alpha particles were deflected, some very significantly. This track shows a deflection through an angle theta. The experiment was actually carried out by Geiger and Marsden, who were working under the authority of Ernest Rutherford. This diagram shows a few typical paths of alpha particles through the gold foil. Rutherford's observations were that most of the alpha particles have small or no deflection, like this one and this one, for instance. But around 1 in 8,000 are deflected through more than 90 degrees, like this one. Some of the alpha particles actually came straight back towards the polonium source. His conclusions, based on this evidence, were that most of the atom is empty space. That explains this first observation of most having little or no deflection. But the atom must contain a small, dense, positively charged nucleus, with the negative electrons around the outside of this nucleus. The small part comes from the small number of alpha particles being deflected. The density, well, if the nucleus didn't have a high density, it would be pushed out of the way by the fast-moving alpha particles. Alpha particles themselves are positively charged, therefore if the nucleus was not positively charged, it would attract and not repel the alpha particles. He knew that atoms were neutral, and therefore they must have negative electrons, making up the rest of the space. Adding nuclei to this diagram, we'd see that there could be a positive nucleus here, for example, causing this close approach alpha particle to deflect back through a large angle, this one which is a little further away being deflected through a small angle, this one much further away showing little or no deflection. The other nuclei would be a long way away from this one. By analysing the number and angle of the deflected alpha particles, Rutherford was able to estimate the size of the nucleus. With higher energy alpha particles, observations no longer matched the Rutherford theory. The alpha particles now were getting so close to the nucleus that the strong force was being felt, and this showed the nucleus to be about 100,000 times smaller in diameter than the atom itself. Niels Bohr made a few adaptations to the Rutherford model to come up with this picture, which you'll be very familiar with, of the small, dense, positive nucleus at the centre and negative electrons in fixed orbits or energy levels around the outside. This diagram is clearly very much not to scale. The electrons would take up a much larger area. Though this model explains many features of chemistry and the world around us, it has since been superseded by a quantum mechanical model, which you'll meet in more detail later in the course.